In this problem, we are given a uniform rod of total mass m and length L. The rod is fixed about this pivot point and is free to rotate about it. Then we have a mass m, a block of mass m sitting on a hill, and this is a frictionless surface. Mass m then slides from the hill with a zero initial velocity, collides with the rod, sticks to the rod, and then with the rod goes up here to the maximum angle theta. The question is, if you know the mass of the rod, the length of the rod, the block mass, and the height of the hill, what is this maximum angle theta that the rod with the block attached to it will make? Now let's introduce two parameters. Let's say that velocity of the block just before the collision is equal to v initial, and velocity of the block right after the collision is v final. Now it is important to note that I am saying this is the velocity of the block just before the collision, and this is the velocity of the block just after the collision. The reason why I have to specify this is because the collision here is inelastic. In other words, some of the energy is lost. And the energy is lost because the block sticks to the rod. So some of the kinetic energy of the block is lost. So again, v final is the velocity of the block right after the collision. So right after the collision, the system, and the system in this case is the rod with the block attached to it. The systems have some kinetic energy, and this kinetic energy is then transferred into the potential energy of the system up here. So let's use that statement and write it mathematically. So the kinetic energy of the system right after the collision consists of two parts. It's the kinetic energy of the block itself, so mv final square over 2, plus the kinetic energy of the rod, 1 over 2 moment of inertia of the rod times angular speed of rotation of the rod right after the collision, squared. Okay? So this is the total kinetic energy right after the collision. At this instant, the potential energy of the system we can take as 0. What happens afterwards? Afterwards, the rod gets to this position, and at this position, the velocity is equal to 0. The velocity of the block and the velocity of rotation are both equal to 0. But we have some potential energy here. How do we calculate that potential energy? Well, we're going to have to look at by how much the block is elevated and by how much the center of mass of the rod are elevated. So the center of mass gets here and the block gets here. So let's first look at the center of mass of the rod. So this is by how much? Now, you should convince yourself that this distance here is equal to L times 1 minus cosine theta. And instead of L, I should say L over 2, because this is half of the rod. So L over 2, 1 minus cosine theta. For the block, however, this distance here is equal to L 1 minus cosine theta. So L, and here it's L over 2. So we can say that the potential energy up there is equal to mg L 1 minus cosine theta plus big M L over 2, 1 minus cosine theta. We can now also relate V final to omega final. Now, V final is the velocity of the block right after the collision when it's already attached to the rod. So, you can say that V final is actually equal to omega final times L. So let's use that in the equation. We also need to know the moment of inertia of the rod with respect to one of its ends. And this is something that is given in the problem. So we can say that this is equal to 1 over 3 ml squared. So let's use that information in this equation now. So you have m, and instead of v final, I'm going to use omega final. So omega final square, L square over 2 plus 1 over 2 I omega final squared. Well, instead of I, we can now say 1 over 3 1 over 3 m L squared, and omega final is there. So this is equal to mgl 1 minus cosine theta plus m L over 2 1 minus cosine theta. Now the rest here is algebra, so I will skip that and I will just write the final expression that we're going to use. So the final expression looks like this. So you have cosine theta equals 1 minus omega final squared L 3 m over m plus 1 over 3g 2m over m plus 1. Please convince yourself, try to work this out yourself and convince yourself that this is what you get from this equation. So, in principle, you can calculate theta from here, but you don't know omega final. So this omega final is what we need to find now. So let's look at this instant when the block collides with the rod. We said that the block gets attached to the rod and therefore the collision is inelastic. But even though the collision is inelastic, because there are no external torques, the angular momentum would still have to be conserved. So we can say that L initial is equal to L final, or I initial omega initial is equal to I final omega final. So what is our I initial? Remember, initial, it is just before the collision. So initially, with respect to the pivot that we have here, the moment of inertia of the system is simply ml squared, where m is the mass of the block, times omega initial, equals moment of inertia of the system right after the collision. So right after the collision, we still have the block so that's ml squared. But now we have the rod as well. So the rod is equal to 1 over 3 ml squared. Omega final. Now, how do we find this omega initial? Omega initial is equal to V initial over L. But what is our V initial? Remember, the block is sliding off the hill. So you should convince yourself that the V initial is equal to 2gh square root over L. So now you have three equations. You have this one, and this one. So you can take this omega initial and plug it in here. So you have ml squared 2gh over L equals ml squared plus 1 over 3 ml squared omega final. So from here we can calculate omega final. Omega final is equal to, again, I'm going to skip a few algebra steps here and I'll just write the final answer. So this is 1 over 3 big M over small m plus 1 times L. If you put the numbers in, you get 1.27 radians per second. So this is the final angular speed. You can then use this in this equation and calculate for theta. So if you do that, your theta is then equal to 32.3 degrees. So this is the maximum angle to which the rod and the block will get to after the collision. So just a reminder again, what are the laws that we have used here? First of all, we use the in this part we've used the conservation of angular momentum during the collision, and then after the collision we use the conservation of total mechanical energy, and that's this part. Now, because the collision was inelastic, you can't say that at the very beginning the total mechanical energy is the same as at the very end.